Hello and welcome back. So far we have seen firstly what soft computing is all about, wherein we discussed how addition of some softness into the problem description, into the problem way the problem is solved, and into the way results are computed, and into the final results, how addition of some amount of softness can yield us systems that can solve problems that no other method in the entire computing domain could probably solve. And hence, we framed in some tools and techniques by which these algorithms were able to solve real life problems. We studied three of these tools and techniques, one being the artificial neural network, the other being the evolutionary computing, and the third being the fuzzy inference systems. Along with that, we discussed something known as heuristics. That was of course the guiding principle, rule, or some set of predefined conventions which could guide the entire evolution process. And hence, using these three tools and techniques from the soft computing domain and the heuristics from the AI domain, we could solve real life problems. We'll continue the lecture series with what is known as hybrid soft computing, or sometimes just referred to as the hybrid computing, wherein we mix ANNs, fuzzy inference systems, and evolutionary computing along with heuristics. We merge all of them to form in systems that are able to solve problems much better. So components of ANNs, they interact with components of fuzzy, components of evolutionary computing, or components of heuristics, or components of themselves, and the limitations get decreased and the advantages gets increased. So what is the limitation of fuzzy system might be what is the that can be overcome by the advantages of evolutionary computing, and the advantages of evolutionary computing can overcome the disadvantages of fuzzy inference systems. So we do a lot of hybridization of systems. We carry forward a lot of hybridization of system where one system or one tool or one technique interacts with another system or another tool or another technique. Sometimes there are more or less more systems out here, out in any relation, in any format, and as a result of this hybridization that is carried forward, we get in some very good real life systems. We get in some excellent systems that solve the problem. The hybridization may be in a pairwise mode, sometimes it's in a master-slave mode, or any of the other modes. Numerous combinations possible, numerous ways in which you can mix into systems. You can combine two systems with complementary skills, with complementary advantages, with complementary disadvantages, multiple ways by which you can mix them all up and make an excellent systems, what are called as the hybrid systems. Now whenever I say that we are trying to create some kind of hybrid systems, one thing needs to be very clear, is that there always has to be a motivation behind the hybridization. There always has to be some kind of inspiration behind this hybridization process. So we need to explicitly state down the characteristics of these systems being hybridized. So there will be a list of characteristics that I'll have of both these systems being hybridized, and after we note down these characteristics of both these systems, we are to analyze what are the shortcomings of this system, and how is it that the advantages of this system can overcome the shortcomings of this system. Will the resultant system of the hybridization be better than my original system out over here? Is it that after hybridization I am likely to get in a system that is better than each of the individual systems. If I am likely to get in a better system, how likely is this likely? Is it just that it might be a fair chance that I get in a much better system, or I'll actually get in assuming computational constraints, real-time constraints? Is it that when I apply both these systems in any of the hybridization modes, I would get in a system that actually solves the problems with this system, or that actually solves the problem with this system? I need to have some motivation in, even if it solves the problem, how is it that this system is going to help the system? Will the resultant system be computationally efficient enough? Because I can mix any system in any of the manner, making the entire picture look very, very complex, which the computational constraints might not allow. It might become so computationally expensive that I might not allow. Is it that the kind of data that I have, does that support a hybrid systems? So once I have this motivation, all that I do is that I draw out some kind of model based on these characteristics, based on the individual weaknesses, based on the individual advantages, based on the individual shortcomings. I make in some theoretical model, which ultimately I implement it up and see whether I'm actually getting a boost or not. I'll see that whether I'm actually getting a boost or not, and then of course I note down whatever the shortcomings of the resultant system, where does it carry forward, where does it lie advantages. And if the entire model has been carried forward judiciously, if this entire procedure has been followed, taking in view your problem description, the problem constraints, your problem requirements, your data constraints, your computational constraints, and all these things, then the resultant model should actually perform better than a one system. So these hybrid systems are like beautiful systems where one system is assisting the other system. One system might be controlling the other system depending upon what model of hybridization we follow. So we'll study numerous up for the next few hours, next few sessions, next few lectures. What we'll be studying in is a couple of the few of these models, and we'll see how hybridization helps in each one of them. In all these models, we'll state what models are being fused and in what manner are they being fused. So just to name a few, we'll be studying today what is known as the evolutionary neural networks, where we carry forward hybridization of the evolutionary computing domain, an algorithm from that domain, as well as an algorithm from the neural network domain, and we make in systems. We'll further extend this talk to the evolutionary neural fuzzy systems, when we carry forward the hybridization of the evolutionary computing, but this time with the fuzzy systems. We might study a bit of fuzzy neural networks, which are hybridization of neural network with the fuzzy system. We'll study something known as ANFIS, the adaptive neural fuzzy inference system, wherein we carry hybridization of neural network with fuzzy systems again. So we study numerous of these algorithms. We even carry forward hybridization of neural network with themselves. These are what are the modular neural network and the ensembles. And in all these domains, we have an evolutionary computing paradigm attached to it. That's why we took in heavy lectures of evolutionary computing. In all these systems, we try to add in some evolutionary computing principles over them in order to have the most optimal architecture of these systems evolving along with time. So that is what is the general principle, the general fundamental of all what hybrid computing is. That will be the agenda for the next few hours of study. The first topic that we take up inside this very exciting field. It's so exciting that the traditional monolithic systems, be it neural network, be it fuzzy systems, or be it evolutionary computing, they have almost disappeared from the domain. They've got almost disappeared from the domain. Now people are not interested with these basic systems. What they are interested in is the hybridization of these systems. What they are more interested in, whether you can make some kind of hybrids of these systems for even better performances, all the benchmark problems for all the simple monolithic systems have been studied, and what is the main agenda of study is that if we can apply in hybrid systems for all these exciting systems that are coming up, for all these exciting intelligent systems of various application domains, whether we can form in hybrid systems of them. So first agenda would be, the first topic of discussion would be what is known as an evolutionary neural network. So of course these are hybridization between evolutionary computing at one end and the ANNs at the other end. What evolutionary neural networks basically are, these are neural networks, but apart from a human designer designing these neural networks, apart from some human specialist, a problem expert or subject matter expert designing these neural networks, we have an evolutionary computing that designs these neural networks. So it's like we have employed evolutionary computing to carry forward the entire design of the neural network, and what finally the evolutionary algorithm gives us is the best, the optimal neural networks that solves the kind of problem that you gave in. So out there in these systems, you just specify a problem, and the entire construction, design, analysis of the solution is done by the evolutionary computing. Now we know ANN is the solution to this problem. The entire design and analysis, the entire working out of the various possibilities is done out by the evolutionary computing domain. Now since I stated that we need to know what are the advantages and the disadvantages of one system so that we can apply the other system as a benefit over the system, so it is important to realize what are the limitations of the ANN. One of the limitations is of course that if it's a multi-layer perceptron, we use a backpropagation algorithm. If it's the other algorithm, we use some kind of Hebb learning from the Hebb's postulates or any other learning algorithm. Now let's repeat our discussion that all these learning algorithms were prone to be stuck at some kind of local minima. So if the problem was something like this is what was my global minima, this was all my local minima, and hence if my neural network is anytime here, it is likely to get stuck here. Even if momentum drives it somewhere around here, it's likely to get stuck over here, it will not reach over here. So that is what is one of my limitations with BPA, to be specific, and in general to all the local learning algorithms employed by any of the neural networks. This is one very strong limitations. As a result, people, what they sometimes say is that make the BPA learn multiple times so that I am most likely to reach up over here, but again does not help, because this entire landscape is highly complex and it's highly dimensional. Because of this problem of complexity and dimensionality, a simple BPA might not be able to give you a local minima. I use the term minima because I have plotted in an error space, not a performance space. So it is most likely to get stuck at some kind of local minima. And because it is most likely to get stuck at some kind of local minima, it's a limitation that we need to solve. A momentum alone is insignificant. A momentum alone is something that might not be able to solve this kind of problem. The other limitation of it would be that who fixes the number of hidden layers, who fixes the number of neurons in these hidden layers, who fixes what connections are to be drawn between the neurons. So far what we had, we said that number one, only one hidden layer. That is what I normally assumed out to be. Normally what we said was that a designer specifies the number of neurons in this hidden layer. So there was a human that we had employed who keeps on experimenting between different number of neurons in the hidden layer. We further had the notation that any neuron was connected to all the other neurons. So it was a fully connected architecture that we were following. Now all these are nothing but things that I have specified to myself. All these are nothing but things that I have specified, and these specifications may not be optimal. These specifications may not at all be optimal, they may be entirely wrong. So out there, when you deal with any real life system, you got in a database consisting of some kinds of inputs and they along with them some targets, and you train this neural network. What happens is that you are to carry forward this training again and again. You fix the neural number of neurons to be 18, carry forward some training. Now because BPA is not optimal in nature, you try to increase momentum, you try to decrease momentum, you try to increase the learning rate, decrease the learning rate, and kind of look at what is the best possible neural network that gives you least error on the testing data, not on the training data. For a neural network having 18 neurons in its hidden layer, then you say might be this 18 is wrong, then you carry forward in 17. And as a result of 17, you get some other performance. You change the epochs, you change in the momentum, you change in the learning rate, you carry forward all this optimization, and then you cannot visualize the trends between a neural network with neurons 18 and the neural network with neurons with 40. So you carry forward more experimentation, you again change the number of neurons. This again creates a lot of problem. Now, since it's creating in a problem, so you repeat the experimentation and you repeat the entire experimentation for multiple hidden neurons, for multiple momentums, for multiple epochs, for multiple stopping criterions, for multiple learning rates and all combinations of them, and still you do not get in any trend. You are not able to visualize any trend so that you can identify what would be the optimal neural network architecture along with the optimal values of weights and biases. What is more depressing is the fact that you train the neural network once for any given configuration. After a lot of experimentation, when you finally come out to check whether this configuration is the best, the most optimal, the best that solves the problem, you get altogether a different answer. So first time you are getting an answer of 95% accuracy for any problem, the next time you get an accuracy of 96%. And between this 95% with the same architecture and 96% with the same architecture at two independent times, there are some 20 to 25 experiments that you have done that lie between the same range of 95 to 96%. So now you're all confused that what is the best neural network architecture, because problem number one is that every time you train the neural network, you get in some different answer. The second problem is that you do not know how many neurons are to be fixed. You do not know what is the learning rate to be fixed. You do not know what's the momentum to be fixed. And as a result, you keep on experimenting, and every experiment gives you a result. It gives you a result that looks almost a random kind of result. It looks almost as if a random result has come out. So you cannot decide what is the best neural network that solves the problem. And since you cannot decide what is the best neural network that solves the problem, a lot of energy is wasted, a lot of time is wasted of a human expert. Now again, because it's a human expert, it takes time to note down the experimental results of one output. It takes immense amount of time to note down these experimental results, repeat the experiments, make it a big hefty table, analyze it to compute what is your next input going to be, to compute what is the next configuration that you will try it out. All this takes an immense amount of time. So for a problem, even if you want to train one neural networks, it would take like an entire day to do so. It would take an entire day to do so, subjected to the fact that 95% and 96% is a hell of difference in accuracy for you. Now today we are dealing with something like 98 and 99% accuracy. So if you can make 98%, 98.5% and 99%, 99.2%, even this difference of 0.2% is very, very significant. So in order to have this additional 0.2% accuracy, you need to carry forward this entire day-long process. This entire day-long process that does only one thing, and that one thing is to decide out of all the various possibilities, that one may have, which one is the optimal neural network. So there's a hell of a confusion over there, and that too because you have to decide the best neural network output for the testing data. So these are more or less what are the limitations of the neural network. So let a human not carry out these exercises, let a human not do all these, let your backpropagation algorithm not carry out the training because it's not optimal in nature. Rather, let the evolutionary computing carry out these, because the advantages of evolutionary computing is a lot of optimization, good learning, and what we call it as a good evolution. Optimization is a very simple kind of word. Now, normally when you keep everything flexible, the entire system architecture as flexible as possible, then you would normally not try to use the word evolution. Optimization, you would try to use the word evolution. These are excellent agents. So we use these evolutionary powers, advantages of the evolutionary computing over here to fill out these limitations. We use these advantages of the evolutionary computing to overcome these limitations of the neural network, and hence the complete problem gets solved. So this is why we would carry out hybridization of the evolutionary computing along with the artificial neural networks. This is exactly the motivation behind carry forward of this kind of hybridization. So now we would like to define what is the basic problem statement of the evolutionary neural network. What is the basic problem statement that we are trying to deal with? I'll go away with this. So the problem statement says that an evolutionary computing algorithm is supposed to evolve the optimal neural network. When I say this, I can mean any model of the evolutionary computing, any model of the artificial neural network, and evolve the optimal neural network means evolve the neural network architecture as well as the weights and the biases. So the problem statement would be that please evolve optimal neural network by an evolutionary computing. So any model over here and any model over here, and ANN evolution would mean evolution of the architecture. So what are the hidden layers involved, which neurons connected to which neurons, and this entire thing. So architecture optimization means I get something like this. This is what would be the architecture of the of the ANN, and plus the corresponding weights and biases. Computation of the optimal weights and biases. We know that to some extent this task was performed by the BPA as well, or the other learning algorithms for the other models. To a good extent, this task was already performed by the BPA, the backpropagation algorithm. This task was not at all performed by the backpropagation algorithm. It assumed a human designer. It assumed a human designer would be sitting who would specify this neural network architecture. But by evolutionary computing, any model over here, be it the swarm intelligence, be it simulated annealing or be it any other model, it will have to evolve both these, the architecture as well as the weights and the biases. So from now on, we'll take in some very specific examples. The entire paradigm of evolution neural network is quite hefty. We'll take in just a few examples wherein we'll specify what the neural network architecture is, we'll specify what the evolutionary computing algorithm is, which may be a genetic algorithm. We'll try to customize it later upon. So there will be limitations upon the neural network architecture, there will be limitations that we apply to the evolutionary computing algorithm to be used, and then is when we would carry forward the optimization under those constraints, under those limitations. So all these would be simple examples that we take under this entire class of evolutionary algorithms. We'll first try to evolve multi-layer perceptron of fixed architecture by genetic algorithm. This is the first example that we take. We'll be using genetic algorithm, and with this we'll be trying to optimize a multi-layer perceptron. Of course, the very next example, I'll go off with the term fixed architecture and I'll make it a variable. So the variable architecture follows immediately after this discussion. So right now the problem statement has slightly changed, the motivation being the same, that remove limitations of the BPA. The motivation is only to remove the limitations of BPA, the other limitation we will not touch upon, to remove the architecture, the human limitation to fix the architecture, that we are not removing. We are only removing one limitation of the backpropagation algorithm that gets stuck at a local minimum. So the problem statement would be that a fixed architecture neural network is already given to me. I already have in hand a fixed architecture multi-layer perceptron. So this is something that has already been given to me. And so on, all these various connections will be there out over here. I already have this thing in hand. I already have in a multi-layer perceptron that comprises of the input layer, the hidden layer and the output layer. I know exactly the number of inputs over here, exactly the number of outputs over here, and exactly the number of connection, exactly the number of neurons over here. So all these three are known to me. Let this be number of inputs be I, number of outputs be O, and the number of neurons in the hidden layer be H. All these are given to me, and most probably we'll assume an all connections approach where every neuron is connected to all the other neurons. So the input is exactly the same that was given to the backpropagation algorithm. This is one input that I have. The other input is of course a training database comprising of some inputs and some targets that is already known to me. So this is known, and the database comprises of some inputs, and along with that some targets that is already known to me. What I'm supposed to do is that I'm supposed to fix values of these weights over here and these biases over here. So exactly the same task that the backpropagation algorithm performs, I have to do exactly the same thing, apart from the fact that in place of backpropagation algorithm, I'll be using a genetic algorithm. So I need to carry forward this training of the multi-layer perceptron using a genetic algorithm. So in my entire discussion, what I'll assume out to be that this is a standard a problem of genetic algorithm, and I'll use this as a means. I'll use exactly the same problem solving methodology as I do with my genetic algorithm. So all these steps that I deal out here, all the steps that I do out here would be the steps that I take to solve any problem of genetic algorithm. I use exactly the same methodology as I do with problem solving in genetic algorithm. So let me remind the problem solving in genetic algorithm. At each and every step I'll briefly discuss how does it apply to this problem, and that will be all for the discussion. Whenever I deal with any problem in genetic algorithm, the first task that I do is known as individual representation, and that is not as a code, but that is at a conceptual level. How do I represent my individual? So let me say that I take in a double vector representation. I take in a double vector representation. The next question that comes up is, okay, that you are taking in a double vector representation, how will you map your phenotype into a genotype? This is my phenotype, a good diagrammatic figure, and this thing I need to convert into nothing but an array of double numbers. So there is a phenotype to genotype mapping. How will you do that? And if I am able to devise this strategy, which is of course not used, this strategy would be naturally the converse of it. So either I draw this strategy or I draw this strategy, they both will be the converse of each other. If I deal with one, the other can be dealt conventionally in nature. So how do I carry forward my representation of a good diagrammatic neural network into this genotype? The other thing that we know is that what comes into the genotype are things that need to be optimized. Whatever thing needs to be optimized, that is embedded into my genotype over here, and anything which does not need to be optimized, that is not represented in my genotype. So in my genotype, I take in all those things that actually need to be optimized. Whatever actually does not need to be optimized, I will not place it in my genotype over here. So the entire this diagrammatic picture, the architecture is already known. So nothing about the architecture, I will place it in my genotype. That is already known, that is constant to the entire evolutionary process. That is something not to be optimized. So what is that needs to be optimized? These are the values of these weights and these biases. These are the value of these weights and these biases that need to be optimized. So my genotype will only contain the values of weights and biases. It will only contain the values of weights and biases. I, H and O are constants. The values I, H and O, they are nothing but they are constants. So let me say that total number of weights, the total number of weights between input layer and hidden layer, they are nothing but equal to I into H. Every neuron here is connected to every neuron here. There are I neurons here, H neuron here. So there will be I into H connections where every neuron of here is connected to every neuron of this place. So there are I-H connections between the input layer and the hidden layer. So what do? I start up from this neuron, I note down this weight. Then I note down this weight, then I note down this weight, then I note down this weight, then I note down this weight. I repeat for this, I note down this weight out over here, this weight out here. So in all I keep on noting down here. The first, this weight comes up over here, let me say 0.5. Then I note down this weight, let me say minus 0.1. I note down this weight, let me say minus 1.0 and so on. So I note down all these weights out over here. And similarly I repeat for all the other neurons. So there will be a total of IH real numbers over here. And what these IH real numbers they would denote is the weights between the input layer and the hidden layer. There will be IH numbers over here that denote the weights between the input layer and the hidden layer. So these parts the weights are done. These parts the weights are done. I move out to this part. They are H neurons. So total weights between hidden layer and output layer will be equal to, there are H neurons here, O neurons over here, so there will be H into O weights here. So I note down this weight first, then I note down this weight, then I note down this weight, then I note down this weight. So this weight, let me say it was 0.25. This weight, let me say it was minus 0.5. This weight, let me say it was 0.8, and so on. The next HO, real numbers that I note down is the weights between hidden layer and the output layer. It is the weights between hidden layer and the output layer. Now because there was only one hidden layer, there was only and only one hidden layer, so this part is done. So here I have represented all weights. The representation of the weights is over. The representation of all the weights is over. I have done in this part of the genotype. So only the weights and biases were to be optimized, so I needed some strategy by which weights and biases can be represented in a genotype from this phenotype solution. I devised a strategy for the weights. I'll repeat up the same strategy for the biases. So let me say that this bias was nothing but 0.8. This bias was nothing but minus 0.5. I note down all these biases out over here. So this would be what will be the bias of the hidden layer. So total number of biases of the hidden layer would be nothing but H. Total biases of hidden layer would be H. So the next H numbers, they denote nothing but the biases of the hidden layer. I am not writing down the biases of the input layer because it's a passive layer, it does not have biases. It performs no computation, it just transfers the input to the other neurons. So I am not writing down the biases of the input layer, they do not have biases. Only my hidden layer and the output layer have biases. Next would be the writing down the biases of the output layer. So there will be a bias here, so I'll write down this bias somewhere around here. So let me say 0.1 and 0.9. These were the two biases out here. The total biases of output layer will be equal to O, the number out here. So the next O will be biases, and this represents nothing but the biases in my system. So what did I do? I made a chronology of these connections, and I kept on noting down these connections from here into my genotype. I had the neural network in hand. I kept on seeing the various connections out there, and in the same order I kept on noting it down in a linear array of the double numbers. After all the weights of input layer to hidden layer was complete, I started the procedure for hidden layer to output layer. That was noted down in this section. After that, I had noted down the biases in this hidden layer. That is what I noted down in this section. And next to come was biases of this output layer. That is what I noted down in this section. So IH real numbers here, denoting the weights between input layer and the hidden layer. HO weights over here, denoting the weights between the hidden layer and the output layer. H biases over here, the biases of the hidden layer, and O biases here, the biases of the output layer. So in all, if I total this up, the number would come out to be IH plus HO plus H plus O. This is what is my size of individual in my individual representation, where every gene is a weight or a bias. The first part of it designated to the weights is the weights, the second part of it designated to the biases is the biases. This is the first part and this is the second part. So in all, this would be what is the size of the individual. That was what was the phenotype to genotype representation, but more converse is more important, you all know. My entire algorithm, it asked me to convert a phenotype into a genotype. It asked me to convert a genotype into a phenotype for fitness evaluation, and hence the converse is important. So what do? I taken this architecture with all random weights. The architecture was already known to me. Since the architecture is already known to me, I need not consult my individual to make in a phenotype to genotype to phenotype representation. Without the individual, I can have this architectural layout. Since I can have this architectural layout, I set all random weights and biases initially. Then I start up with this 0.5. I exchange this bias weight by 0.5, minus 0.1, I exchange this by minus 0.1, minus 1, I exchange this with minus 1. And I note down all the weights between input layer to hidden layer first, this part. Between the hidden layer to the output layer, this part. I set the biases of the hidden layer, this part, and the biases of the output layer, this part. And then is when my problem is solved. So the first part of it dealt with how do I represent my individual. I have converted my individual using a strategy into a genotypic solution. The second thing is that how do I calculate the fitness of this individual? That is the second question we normally ask whenever we are dealing with the genetic algorithm, is that how do you compute the fitness of your individual? And that is again simple. Fitness of an individual means I have to write down a function known as fitness of I. So all that I do out in computing this fitness is that I convert I in its genotypic solution to a neural network that into its phenotypic solutions. This is what is an A and N. Since this is an A and N, I pass the training data into this A and N. So I pass the training input into what is, I got this as the A and N. I get the output out over here. I already have the targets out over here. I calculate the difference, and that is what is an indicator of my fitness. If it's error, I'll call it as the cost. If it's performance, I'll call it as the fitness, subjected to whether I have to maximize it or minimize this. Normally we take error, so normally we calculate the cost. Normally I take in the error, how much my outputs deviate from the targets. Normally I calculate this error, and of course this is exactly similar as we calculate the error in terms of backpropagation algorithm. So I may not repeat this formula where it would be from I equals to 0 to n the size of the training data. It will be output that is produced by my ANN. So it will be ANN whenever it's given any input I minus the target, corresponding target. If it's a mean square error, this is what I wrote down divided by n, that will be what my error would be. If I'm writing down it as the error, I'll say this is a cost. Same notation of fitness, except from that it will be termed as a cost. So my second part is done, that I've calculated some kind of fitness. So I've done two things over here. I have formulated in a strategy by which I represent my individual. I have formulated the strategy by which I represent an individual. And the second thing that I have done is that I have made in a fitness function. The third thing that I need to do is to have genetic operators. Now because my individual is a double vector, so all the conventional operators would apply. That means I'll be able to use conventional selection, I'll be able to use the conventional scaling, I'll be able to use conventional crossover, I'll be able to use conventional mutation, and I'll be able to use conventional elite. So my third part is done by default. I need not do anything out over here. All these things have already been done. When I've got my conventional genetic operators that come into the picture over here. And that of course means my problem has been solved. So whenever dealing with a fixed architecture neural network, all that we are supposed to do out here is that we are supposed to make it a problem representation strategy. After that, generate in random individual, define a stopping criterion. Once we define in a stopping criterion, then what we are supposed to do is that we apply all the genetic operators that are all conventional in nature, and after that have the fitness measure. The fitness measure would be very simple: convert it, reverse into the neural network, pass in the training database, get the outputs and calculate the error. Now, one thing that unfortunately happens out over here is that my training database size is usually large. Because any neural network it would require a hefty amount of database that it can fundamentally learn. Learning small amounts of data is no innovation. Now my database size is large, so all that my fitness function is, it says sometimes that for every input comma target in database, and then there is a computation of error out over here. Now this loop becomes very heavy. This loop becomes very heavy, and therefore, as compared to the conventional genetic algorithm, the evolutionary neural networks are much slower. And why are they slow? Because suppose you take in randomly 100 individuals for 1000 generations, so total number of fitness evaluation would approximately come out to be 100 into 1000, that means 10 to power 5, and that means they are 10 to power 5 computation of this hefty fitness function, which might ideally not be possible. So you need to cut the number of generations, you need to cut the number of individuals. So much of computation is not possible. So much of computation is not at all possible because my database size is large. If database size is large, then this is a very heavy loop that is repeated for as much as 10 raised to power 5 times. Now because of this, what happens is that evolution cannot continue in its natural format. I might get suboptimal results because of these limitations. And that is why there is something very exciting in evolutionary neural network. How do you control the time factor? So this is one of the problems. The second problem that we face is that in the entire genetic algorithm we had the conventional genetic algorithm or something simple genetic algorithm. What we had sometimes assumed was that the fitness landscape is simple, and because the fitness landscape was simple, something like this, the various individuals out here, they could easily converge into the global minima out here because escaping this local minima is very simple. These would converge somewhere around here. There will be an excessive population out in this region, but at the same time these would converge out here, and whenever these individuals cross this line, this algorithm would get, individuals would get fitter, all less costly because it's a cost landscape, and then the entire convergence would go about over here. So it was very simple. But this does not happen when I deal with the problem of evolutionary neural networks. So if this is an evolutionary neural network, imagine in this error scape or this cost landscape, the dimensionality is the size of my individual. The dimensionality is the size of my one individual. So that means the dimensionality for the same problem that we had considered was nothing plus IH plus HO plus H plus O, taking approximately H to be 15 and O to be approximately 1. You can calculate that this comes out to be approximately, and I'll have to specify I to be, let's say, 10. It comes out to be approximately of the order of 200, which is a very high amount of dimensionality, which is an excessively large amount of dimensionality. And then this is a very simple problem that I have taken. This is a very simple problem. My actual problems would have dimensionality of much larger than that. And in simple genetic algorithm, what we were dealing with, dimensionality of 10, 12, 15, 20 and not 200. So dimensionality is very high, the problem is very complex, and simple genetic algorithm fails in such high complex problem because of what we have already discussed. The dimensionality is high, so the error space is very large in size. It's very sensitive, So I can have something like this as my error space. It's very large in size, it's very complex, you can only judge a small percentage of it, you can only evaluate a very significantly small percentage of it. Again a problem. So simple genetic algorithm alone might not be enough. Now remember, it was only the addition of neural network and evolutionary computing in this technique. This is also not able to solve this problem. And of course the other problem is that we have already curtailed the individuals, we've already curtailed the generations, so both of them have been curtailed. So algorithm will be much more suboptimal in nature. Complex fitness landscape, extremely complex error space, low individuals, low generation. So how do we deal with it? We apply some kind of heuristics. We apply in some kind of heuristics in order to solve this problem. And how do we apply heuristics? That we say that whenever an individual is there anywhere in this error space, we will not return this error value, we will not return this error value. This is not the error value that we will be returning, rather we will be applying a very few iterations of a local optimization algorithm. We will be applying in very few iterations of a local optimization algorithm, and what a local optimization algorithm will do is that whenever this individual is given to a local optimization algorithm, it will at very small instances of time place it here. When this individual is given, it will at very small instances of time place it over here. When this individual is given, very soon it will place it over here. One example to it, the backpropagation algorithm. If I apply in a few iterations of backpropagation algorithm with very low magnitude of momentum, I need not escape from a local minima, that's not my intention out here. It's an intention to a fairly low level with very low value of local momentum and a decent value of learning rate. This will do that. It will place this somewhere around here, it will place this somewhere around here, it will place this somewhere, might not be here. This would require larger iteration, but somewhere around here. So all the individuals, they are taken by a local technique and they are it returns their best possible, the nearest possible optima. So as a result, what happens is that whenever my genetic algorithm sees this, it does not see this fitness landscape, it does not see this cost landscape. Rather, what does it actually see is that there was an individual over here and it was reported an error over here. There was an individual over here, it reported the same error roundabout here. So it sees something like this, which is a much simpler landscape. This individual will report an error over here, and then there might be multiple individuals reporting multiple error. So this is a much simpler cost landscape. That is what it sees. Because how this cost landscape is constructed for various values of weights and biases, here it was only the weights and biases. For various values of weights and biases, I see what the error is, I plot it up graphically. So even though my actual error is here, what my function is returning is this error, and therefore this complex landscape, if there was an individual over here and I'm using some kind of local optimization technique, it will place it here. Every local optimization has got some global nature, so it will escape from here, it will come up over here, and this is what it will report. It might eventually escape this as well and come out over here. Backpropagation algorithm is one example of a local optimization technique. The other is called as simulated annealing that we've already seen. Simulated annealing is again a very famous example of local search strategy, local optimization, and both of them are uni-agent. So with this we also realize what is the potential of uni-agent. So whenever I am writing down a fitness function out here, my fitness function for any individual I will be that first of all I get its phenotype. I get its phenotype solution. I apply some local search strategy. So let's say I get in a local search, which is a BPA or anything, and then I return fitness or a cost of this I double dash. So that is what my algorithm modifies to. And this local search strategy, it does one very good thing, that it simplifies the fitness landscape. Now here we are dealing with three things. Firstly, the problem is evolution neural network, so we are dealing with neural network. Ultimate goal is to evolve a neural network. Secondly, we are using evolutionary computing, so all the paradigm of genetic algorithm, but we said that genetic algorithm here has some limitations. So we are using the third paradigm that is known as heuristics, which is in form of a BPA or a simulated annealing or any local search. We are using this exciting thing called as heuristics to guide, to orient, to strategize the mechanism in which the search is applied. We are strategizing the local search by using this paradigm of heuristics. So that's a very, very exciting system called as the evolution of neural network with this architecture. I'll not repeat any single instance of my earlier discussions. I'll not revisit any discussions of my earlier discussions that I took regarding the use of BPAs. Any individual out here, so it's like the individuals, they keep on moving along with time. They keep on moving along with time. Any cross over here is nothing but, any cross out over here is nothing but a neural network. When given a problem, it gives me a problem. So if this was my training database, any cross over here means nothing but something like this. This is what my ANN plots. And of course, multiple individuals, they mean multiple neural networks out here. So there's an ANN1, there's an ANN2, this is nothing but GA individual 1, GA individual 2, and I get this entire fitness landscape in this mechanism. I get out this entire fitness landscape, I get out all of these individuals in this mechanism. So if I plot only the optimal best neural network, best individual, if I only plot the best individual over here at any generation, I'll see that this curve is getting more and more closer towards the ideal curve like this. It will get more and more closer to the ideal curve. So if only seen in this space, which is the problem space, if seen only in this space, which is nothing but my problem space, what happens is that the predicted curve, it keeps on getting closer and closer towards the ideal curve as we move along with generations. It keeps on improving along with time. It keeps on improving along with time. The other error space that I have is that this location, basic structure of the genetic algorithm will follow, where this is the worst, this is the best, and this is the average performance. So this was about the evolution of fixed architecture neural network. The next what we'll take is the evolution of variable architecture neural network. That will be at the next hour.